Alright, this is part 2 of the video for 7.2 and 7.3. We had left off last time with the washer method, and we're going to continue on with that one. This one's asking you to revolve the area that's bound by y equals x squared and y equals 2x around the y-axis, finding volume. So, if we graph that, alright, so we're basically talking about a graph that looks like this. Here is y equals x squared, of course, will be a parabola. I only drew the parabola on the right side because I knew it had to be the enclosed area between the parabola and this line. The line is y equals 2x. That means it crosses at the origin and has a slope of up to over 1. And so if you're having trouble seeing the parabola, think about it coming around to this side as well. Alright, so the area enclosed by those two would be this little strip right in here, which I'll kind of shade in yellow. So that is the enclosed area. So now I have to take that enclosed area and I have to spin it around the y-axis. So if I spin it around the y-axis, think about this area. If I was going to take this area and stack rectangles up in it to find area, would I? Which way would I do it? Theoretically, I guess I could go either way, but if I have to revolve around the y-axis, I'm going to have to make horizontal partitions so that when it wraps around the y-axis, I get washers. There's no really a way to make a disc, but as I wrap these around, these little partitions around the y-axis, I get all these washers, and those washers stack up from the bottom to the top, and I'll bring in a picture to show you what that looks like. Alright, and so here is a 3D of what this picture would look like. This is your little rectangular horizontal partition that I have drawn right here, and you can see as you spin this blue shape around the y-axis, you can kind of see the shape that it makes. And here is one of your washers. So we know we're going to need to use washer method for this. And the fact that we have a horizontal partition, anytime you have a horizontal partition, you know that means the problem means a dy. So we have a dy problem. So we have an integral with a dy, and remember the formula for the washer method. It was pi outer radius squared minus pi inner radius squared. So if you think about where the outer and inner radius would be, think about kind of down here on this 3D picture. Your outer radius is going to be the distance from the y-axis over to here. And your inner radius of this washer would be the distance from the y-axis over here to the inside of the washer. So in order to get the area of the ring, you need the outer minus the inner punched out. It's like a full circle, and you're subtracting out this inner circle. So outer radius, if you look at this picture, the outer radius would be the distance from here over to here. And the inner radius would be the distance from here over to here. So how do we figure out what those are? Well, think about that. The distance from here over to here would be the x value for a point on this purple curve. So imagine a point right here on the edge of the curve. Okay, this point has an x value and a y value. That point there has an x value and a y value. And I am looking for the x value. My outer radius is going to be x. But remember, this formula is only allowed to use y's. So I have to do, remember the purple represents this equation right here, and I don't have something for x, so I need to solve for x and write it in terms of y. So I know this point is x comma y, and x, the distance from here to here, is my outer radius. And so I know that for this problem, y is equal to x squared. So if I solve that for x, I would square root both sides. And if I square root both sides, I get x is equal to the square root of y. So since my outer radius is x, and I can't use x because I'm supposed to use y's, I will use what x is equal to, the square root of y. So remember my formula is pi times the outer radius squared minus pi times my inner radius squared. So now I got to figure out what my inner radius would be. Well, the inner radius would be the distance from here to here. And the distance from here to here, or here to here, or here to here, anywhere it's going to become larger as I go up, but it will always, 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 always be the x value for a point on this red line. So the x value, you think about a point on that red line, let's say this point right here, from here to here, is the x value of that point. And this line is y equals 2x. I need to know what x is equal to because I can't use x's in my formula. X would be equal to y divided by 2. So my inner radius is y divided by 2. So I'm going to have to work this out to find my area. And keep in mind, we need to know we're going from where to where on this thing. So I'm going to go from here up to here as far as how I'm going to stack these little rectangles. These rectangles stack horizontally from 0 up to 4 on the y-axis. If I have a dy, I have to use y-axis numbers, so 0 to 4. And so now we'll go to the next page to work that out. All right, so here's the integral that I need to work out. I could factor that pi out since it's just a constant and put it out front. And then the square root of y squared would be just a y. And then if I square both of these, I get y squared over 4, or 1/4 y squared, whichever way you want to write it. All right, so simple integration now that we've got it set up. So I'm going to have a pi times a y squared over 2 minus y cubed over 12, because I would take 4 times 3. I already had a 4 there, add 1 to this and divide by that 2, that's how I got the 12. And then I need to plug in the numbers from 0 to 4. So if I plug a 4 in there, I'll have 16 divided by 2, which is 8. And then plug 4 into here. 4 cubed is 64. So I end up with 64 over 12. And I plug in 0, and of course if I plug in 0, that would give me 0 on both. So simplifying 8 minus 64 twelfths, if we reduce the 64 twelfths, divide them both by 4, I get 26 on top, 3 on the bottom, so I have 8 minus 26 thirds with a pi out front, so that would be 24 thirds. Alright, so I made a mistake here on this 26. 64 divided by 4 would not be 26, it would be 16. Thank goodness, because that makes the problem come out with a positive area or volume, which we would want to happen. So that's going to be 24 thirds for the 8 minus 16 thirds, which is equal to 8 thirds pi. So 8 thirds times pi represents the volume of that figure. All right, so in this problem, they want you to take this parabola, this line, and bind the area that they close off. So we'll start by doing that. The parabola 9 minus x squared means that parabola shifted 9 up and flipped upside down. So I've got half of that drawn here. It would also exist on this side over here. But they want specifically the area that's bound by those 3 things. And so we'll assume that they want the area on the right side and not the left side of that axis. So if I draw that in there, here's my parabola. And then I have the line x equals 0. That's a vertical line crossing through the x-axis at 0. So that would be this line right here. And then they have the horizontal line, y equals 0, which means cuts through the y-axis at 0. So that would be this line. And I'm just drawing in the part that encloses off that area. So this is the area that I'm talking about, enclosing. I can shade that in yellow. And now it wants me to take this area, and it wants me to revolve it around the line x equals -2. So they want me to revolve it around this line right here. And so you're going to take this, all of this region that's in yellow, and spin it around this green line to make a three-dimensional solid. And of course you're going to need horizontal partitions to get a washer out of that. So around and around and around, here would be one individual washer that you would make from doing that. And I'll see if I can bring in a picture for that. Alright, so here's a three-dimensional of what it would look like if you took this thing and spun it around. And it's drawn to a little bit different scale here, but here's the y-axis, and here's the x-axis. Here's your parabola, and so right here is the region that I have drawn in yellow. So if you take that region that I have drawn in yellow and you revolve it around the line, x equals -2, you get this almost the shape of a bundt pan, baking pan, or something like that as you do that. And you can see there's this hole in the middle. And that's what happens, of course, when you have washers. And so here's one washer ring going around. Think about that little tiny rectangle I drew here. Spinning it around would make this washer, and so that's why we call this the washer method. So I'm going to need to use the formula for the washer method, which is pi times outer radius squared minus pi times inner radius squared. And so if you remember me talking about, it's a lot like in the 7.1 how we did top minus bottom and right minus left. The outer is always like the right, and the inner is like the left. But you have to be careful, because this one's not just going around the axis here. Think about my outer radius. My outer radius would be the distance from this vertical line all the way to the outside of the washer. So from here to here. So we know this distance right here is a distance of 2. And so I'm going to need to add 2 to my to this length right here. Now it looks like no matter how far up or down I go, the inner radius is always going to be a distance of 2, because this is just a straight line. And so that would always be a 2. So my outer radius is going to be the distance from here to here. So that would be 2 plus whatever this length is here. I'm going to draw that in a little bit straighter. So this length from here to here is 2, and the length from here to here is x. So from here to here is the x value of that point. So this total length right here is 2 plus whatever x is on this curve. So essentially 2 plus x is my outer radius. But remember, I have to write this with y's because I have horizontal partitions. Anytime I have horizontal partitions, I'm going to use a dy. So I've got to write this 2 plus x. I've got to change x on this curve to something with y's. So go back to that equation, which was here, and solve it for x. So if I solve that thing for x, y is equal to 9 minus x squared. That's going to be y minus 9 equals negative x squared. Change my signs, and then square root both sides. I end up with x equaling the square root of 9 minus y. And so that's what I'm going to replace this x with so that I can use it in my formula. Again, we're finding the outer radius, which is 2 plus x, but I can't use x this is a parabola, so I'm going to use this formula and solve it for x, so that I can write x in terms of y. So now I'll plug that in right here. So I've got 2, I got pi times my outer radius. My outer radius is 2 plus the square root of 9 minus y, all squared. All right, and now I have to subtract the inner radius squared. So my inner radius is simply the distance from here to here. And it will always be a 2 no matter what, just a plain old 2. So that's going to be a pi times 2 squared. All right, so I have pi times outer radius squared minus pi times inner radius squared. And so now that's the problem I got to work out, and I will do that on the next page. All right, so to integrate this, once again, you can pull your pi out. This one's the most complicated part right here, is you actually have to work this out. And to do that, you're going to have to square the first, square the last, multiply, and double. So if I square the first, I will get a 4. I multiply these two things together and double that. I will get 4 times the square root of 9 minus y. And then square the last. When I square a square root, the square and the square root cancel, and I'm left with just a 9 minus y. So that's all of that. I've already factored this pi out, so I have a minus 4 on the end for that 2 squared. So all of that has a dy on it. All right, so it looks like this negative 4 and positive 4 right here will cancel. And then I will be left with an integral that looks something like this. 4 times 9 minus y to the half power plus 9 minus y. All right, and so now I'm ready to integrate. Now, you basically have 3 separate terms to integrate. These two are going to be easy. This one's a little more complicated, but not bad. You can say let u equal 9 minus y. And remember, if you do that, the derivative of that would just be a negative 1. So it's just going to change your result by a negative. So rather than going through the whole u process, if you just want to divide by a negative 1 to adjust it, you can. So integral is going to be, I'm going to have my pi out here, 4 9 minus y, add 1 to the half, and you get 3 halves. So I need to divide by 3 halves, and I also need to divide by a negative to adjust for basically backwards chain rule. If I was doing a derivative, I would multiply by negative 1. I'm going backwards, so I'll divide by a negative 1. All right, next term is going to be 9y, and the last term will be y squared over 2. And now, what am I going to integrate from? I never found my numbers that go over here. If you look back at the picture, these rectangles would stack up from 0 all the way up to 9. So we're going to go from 0 to 9 on our integral. And so now I need to plug those in and maybe simplify this. If I flip and multiply here, I'm going to get an 8/3. So I'm going to have 8 times the square root of 9 minus y cubed all over 3. And I can pull that negative out there. All right, so I also have a 9y and a minus y squared over 2. And I need to plug in from 0 to 9. All right, so when I plug in the 9, I'm going to get 9 minus 9, which is a 0, which is going to wipe out this whole term. Plug a 9 in here. And I'm going to get a 81. Plug a 9 in here, and I'm going to get 81 halves. All right, now I'm ready to plug in 0. So if I plug in 0, I am going to get something here. It looks like I'm going to get a negative 8/3 times the square root of 9 cubed. Negative 8/3 times the square root of 9 cubed plus 0 plus 0. So at this point, that is what I have. And so to do the square root of 9 cubed, think about that. I have the square root of 9 cubed, which is the square root of 9 squared times 9. So, because you just add your powers to get the 9 cubed. So the square root of 9 squared times the square root of 9. The square and the square root cancel out here, and I just get a 9. The square root of 9 itself is 3, so 9 times 3 is 27. So this little thing right here comes out to be a 27. And so we'll go plug that in there. So now I have pi 81 times 2 is 162. So I would have 162 minus 81 over 2 for that, which would be 81 over 2. And then over here we said this comes out to be 27. So I have a negative 8/3. And honestly, this negative that's here, I can combine these two and make a plus. And so I have 8/3 times 27, which 27 divided by 3 is 9. So I end up with 9 times 7, which is a 72, plus 81 halves when I take 162 minus 81. So common denominator for that, I'm going to have 81 plus 144 over 2, all times pi, and 144 plus 81. So that will give us 225 over 2 times pi, and so that is going to be my volume for that crazy figure there. All right, next example. And so now we are ready to move on to the shell method, which is the last method you're going to learn for finding volume. And so here's kind of a generic view of how the shell method works. Imagine you have a function that's been given to you, some function f of x. They don't tell us what this function is, they just call it f of x. And let's say you bind it with these two vertical lines and the x-axis, and then you take that region and you revolve it around the y-axis. And so if you were to do that, take this region right here and you revolved it around the y-axis, this time you would get basically a figure that looked like this if you did that, and it looks like you'd have a hole here in the middle where this is cut out. But anyway, to make shells, it's a little bit backwards from what you've been doing. You would need a vertical partition right here, and if you're taking that vertical partition and going around the y-axis, that vertical partition would make a shell that looks something like this. So here's the little vertical partition, and you take it and you revolve it around the y-axis to get this, what they call a shell. It's kind of like a thin roll of duct tape. If you could imagine a roll of duct tape that hardly had any tape left on it, that's kind of what a shell would look like. Where a washer is flat. This is not flat, it's tall and thin. And so if every one of these partitions that you drew in this original region was revolved around the y-axis, you would end up with something that looks like this. And so now what we're doing is we're taking all these shells and adding them up to make this figure. And so the shell method, if you go look at those formulas back on our page. All right, so here's your formula sheet. Shell method is given down here. We just finished doing washer and disc. And remember, all these question marks are H's. For some reason, those come off as question marks. So, the formula is very similar to circumference, which is 2 pi r times height. So think about if you were to do the circumference or the area of the label on a vegetable can. Remember, if you unroll the label on a vegetable can, its area would be circumference times height. This formula is kind of like that. So you've got 2 times pi times the shell radius times the shell height. and of course a dx on there to get your volume. Now this one's a little bit backwards from what you're used to in the other one, but the one thing always holds true: if you have a vertical partition, you will have a dx. If you have a horizontal partition, you will have a dy. That holds true for every formula on this page. So if you look back over here at this, we had a vertical partition. And remember, vertical partitions when we were doing washer and disc typically meant you were revolving around a horizontal line, but with the shell method, you're revolving around a vertical line. And so that's the one thing that's a little bit different. But always, always, always focus on your partition. Is it vertical or is it horizontal? This is a vertical partition. Vertical partitions always mean dx. So that means I would be using this formula right here with x's, even though I'm revolving it around a y-axis. All right, so I wasn't given a formula on that one. That one was just a generic one. So we'll go on and do an example. All right, so here's our first shell example, and we're going to revolve this polynomial function around the y-axis between 0 and 1. So this one's a little tougher in the sense that we probably don't know what the top of this one looks like off of the top of our head. Now, it would be okay to grab your calculator and graph it to figure that out. We're going to try and do that on this problem without it, just to practice that and refresh some of our college algebra skills. So if you think about, usually polynomials look like some sort of roller coaster. So remember, I only am concerned about this graph between 0 and 1, so that could help me a lot in terms of narrowing it down. So if you think about between 0 and 1 on the x-axis, let's make this 1 and this 0, and think about on this function, what would its y-intercept be? Remember, anytime you want to find a y-intercept, you let x be 0. So if I let all of these x's be 0, these would all go away and I'd have y equals 1. So I know this thing crosses the y-axis at about 1. So I now have a y-intercept here. Now, x-intercepts are more difficult to find, because to find an x-intercept, you have to let y be 0. And if I want to let y be 0 and try and figure out what x would be when y would be 0 without looking at my calculator, the first thing I would try, it would be a 2x2 box. There's 4 terms, so I would try putting all 4 terms in a 2x2 box, and I would try it and see if it factored out to something nice. And I tried it already, doesn't work. So that method's not going to work. That's called factoring by grouping when it does work. So your next option would be to try and find numbers that you could use synthetic division with that would hopefully give you a 0 when you use synthetic division. Now, what really helps me on this problem is I know I'm only concerned between 0 and 1. So these are the only 2 integers I have. So I know this one doesn't work because my y-intercept came out to be 1. So I could potentially have an x-intercept at 1. Anything other than that, I don't really care if I got an x-intercept at 2. That doesn't help me because I'm only concerned about what happens between 0 and 1. So if 1 happens to work, that would be a huge plus. So I've got -2. Put your coefficients down. Going to refresh your memory on synthetic division. That's why I wanted to do this. I want to pull down this -2. Multiply these together. That gives me -2. Add these together. That gives me 1. 1 times 1 is 1. -2 plus 1 is -1. -1 times 1 is -1. And I get a 0. So, I did get a 0. And so what does that tell me? The fact that I got a 0 here means that this is in fact an x-intercept. So I do have an x-intercept here. So I don't really know what this thing looks like, but it looks something, some curve in between there, whatever that curve may be. So I'm just making some sort of a curve between those 2 points that I know the graph goes through. And so now I'm going to revolve that around the y-axis, and I'm going to use the shell method here. So to use the shell method, I'm going to need vertical partitions to get shells. So we're going to take each of these little vertical partitions, wrap them around the y-axis, and I'll have a bunch of those, and I'll eventually get a 3D shape, which I'll bring in a picture for. Alright, so basically, if you take this and revolve it around the y-axis, you get this Hershey's Kiss looking figure over here. And they've only got one of the shells drawn in for you, the one that would kind of correspond to this partition here. Remember that a shell is kind of like a roll of duct tape with hardly any tape on it. And so we've got a bunch of those, some would be taller than others, and stacking up to make this figure. So remember the formula for shell method is integral of 2 pi shell radius times shell height. Now the question is, are we using a dx or a dy? It's all in the partition. Anytime you have a vertical partition, that means your problem is a dx problem, which means I can only use things with x's in here. I cannot use anything with y's. All right, well, let's think about that. Your shell radius and your shell height. Well, the shell radius would be the distance from here to here. And as your shells change in size, here to here, here to here. But it will always be from the center out to this polynomial function. And so this point right here or right here is kind of what you're referencing. So my shell radius would be the distance from here to here, which is the x value of this point, the x value of this point. And your shell height, the height of this shell, is going to be the y value of this point. So the shell radius is the x value of this point, which I can just use x because this is a dx problem. So x is just x for my shell radius. Now shell height, the height of the shell is the y value of this point. I wish I could just put a y here, but I can't because this is a dx problem. I have to put something that y is equivalent to. Well, y is equivalent to this, and this has x's in it, so that's what I'm going to use for my shell height. So for my shell height, I use negative 2x cubed plus 3x squared minus 2x plus 1 with a dx on it. And so that's basically the integral that I have. And how would these partitions stack? They're going to stack from 0 to 1. So that's what I set my integral endpoints at. All right, and then we will work that out on the next page. All right, so this thing I now need to integrate, and before I integrate, I'm going to want to multiply this x through here. I can pull the 2 pi out because it's just a constant. So that would be negative 2 x to the 4th plus 3x to the 3rd minus 2x squared plus x dx. And now it's just backwards power rule on all of them. Not hard, just several terms that we have to do. So we are going to end up with a negative 2x to the 5th over 5 plus 3x to the 4th over 4 minus 2x cubed over 3 plus x squared over 2 from 0 to 1. And so now I just need to plug in my 0 and my 1 and multiply everything by a 2 pi. So if I do that, I plug in the 1, I'm going to get a negative 2/5 plus 3/4 minus 2/3 plus a half. Lots of fractions there. And then if I plug in the 0, I'm going to get 0 in all of them. So now I need a common denominator for 5, 4, 3, and 2. Which 5 and 4 would be 20, but 3 will not go into that. So 20, 40, 60 would probably be the next one that they would all go into. So if we have a common denominator of 60, that means I'm going to multiply the first one times a 12. So that's 24. 4 times 15, so 3 times 15 is 45. 3 times 20, so 2 times 20 is 40, and then a 30. Hopefully I haven't messed up the math there anywhere. All multiplied by a 2 pi. I could reduce the 2 and the 60 if I wanted to make that a 30. And 45 minus 40 is 5. 5 and 30 is 35. And 35 minus 24 would be 11. So I'm going to end up with 11 over 30 times pi. Got the 30 from reducing those, kept the pi, got an 11 from simplifying all this. So there is the area, 11/30 times pi, of that specific figure. I might point out to you also that this problem could have been done with a disk method as well. You wouldn't have to use shell on this, but notice how much more difficult this one would be if you had a disk. If I did this with the disk method, I would have had a horizontal partition right here, and then when I take that horizontal partition and wrap it around the y-axis, I would have gotten a disk. And so I would have had all these disks that stacked from 0 to 1, but I would have had to use y's because it was a dy problem. And so if I were doing this with y's, using the disk method is pi times radius squared. And so pi times radius squared, horizontal partitions mean dx's. So it starts out looking pretty good, but you think about this radius, the radius of this disk would be the x value of this point. So the x value, if you think about it in terms of this function, what is x equal to in terms of this function? I don't really know. This function is y equals negative 2x cubed plus 3x squared minus 2x plus 1. And that would be a pain, a real pain to try and get x by itself. But that's what I would have to do to try and use the disk method. So every shell problem can also be done with either washer or disk. It's just a matter of which one makes the most sense and is the easiest. Alright, so in this one we're going to revolve the region bound by the square root function and the cubic function, and then we're going to revolve those around the x-axis. So let's see what this would look like. The square root function, I've got a graph going right here. Notice I made the scale a little bit bigger so we could kind of zoom in and see what was going on here. This is 0, this is 1, this is 0, this is 1 on the y-axis. So the square root function, remember, is that one that comes up out of the water and does this. So that one is kind of going to look like this. And maybe I should make that a little bit more rounded, something like that. And then the cubic function goes the other way. It looks kind of like this. So we're talking about this little sliver right in here, and we're going to revolve that around the x-axis. So taking this little pedal here and revolving it this way. And I'm going to use the shell method. This is once again a problem that could be done using the washer method. You could put a vertical partition here, spin it around and make a washer, or we can do a horizontal partition and make shells. And we're trying to practice the shell method right now, so we'll make this little horizontal partition right here. And imagine taking that partition and revolving it around the x-axis until you had like a roll of duct tape lying on its side. And then you would have a bunch of those to make a picture. And I don't really have a picture of this one, so we're just going to imagine what that would look like. And so if I'm using the shell method, I used a horizontal partition. Remember that horizontal partitions always mean that we're using dy. We're going to use y's in our formula. And these little partitions would stack from here to here. So that means we are going from 0 to 1. And remember, the formula is 2 times pi times the shell radius times the shell height. And so my shell radius, remember this thing is revolving around like this, so the shell radius is going to be the distance from here to here, or here to here, which would be the y value for either function. Notice it doesn't matter where you're at, wherever your partition's at, if you're on the green curve or whether you're on the blue curve, that y value is still going to be the same. right? The y value for the green curve right here is the same as the y value for the green curve right here. And this is a dy problem, so I can just use y for my shell radius. And once again, think about what this is going to look like. This is a roll of duct tape that's sitting on its side, like if you were to set it on a table, it would roll around. And so our radius is from here to here. The height of our roll of duct tape, we might be better off to call it the width, because it's going to look like a width. It'd be the distance from here to here. All right, so if I rewrite this, I'm still from 0 to 1, 2 times pi. We said the shell radius was y. Now the shell height, or width, is the distance from here to here. Now, how am I going to write that mathematically? The distance between here and here. Well, if you think about that, I could write it as saying, hey, it's this length right here minus this length right here. So if I were to take this distance and subtract out this distance, then that would leave me with this distance right here. So the distance from here to here is the x value on this curve, and the distance from here to here is the x value on the green curve. So I need the x value on the blue curve minus the x value on the green curve. And remember, I'm only allowed to use y's, so remember that the blue curve is the cubic function, right? So the cubic function, if I write it with, reverse that and solve it for x, what would x equal? So remember, I'm trying to get x on the blue curve minus x on the green curve. That's basically what my shell width or height is going to be. It's going to be this distance minus this distance, x on the blue curve minus x on the green curve. So x on the blue curve is the cubic function. Guess I should write that in blue. So now if I solve for x, I'm going to cube root both sides. Cube root of x. So x, so essentially here's what I have. 2 times pi times my shell radius, which we said was just a y, and then my shell height or width, however you want to think about it, which would be the x on the blue curve minus the x on the green curve. Well, the x on the blue curve is equal to the cube root of y. So I can replace, because remember, this is a dy, I'm only allowed to use y's here, not x's. So I'm going to rewrite this, 0 to 1, 2 times pi times y times the cube root of y, which is y to the 1/3 power, minus the x value on the green curve. Well, the green curve is the square root function. And so if you solve it for x, you would have to square both sides. So if we square both sides of this function, we would get x equals y squared. So this x is a y squared. And now I have a problem with nothing but y's that I can actually work out, which I will do on the next page. All right, so we will multiply this out. So take y times y to the third. That would be y to the 4/3 and y cubed here. All right, so now I'm going to pull out my 2y, and I will be ready to integrate at this point. All right, so y to the 4/3 plus 3/3 would be y to the 7/3 divided by 7/3. When I flip and multiply, would become a 3/7. And then y to the 4th over 4, plugging in a 0 to a 1. So when I plug in the 1, I get 3/7 minus 1/4. Plugging in 0 would give you 0. So essentially, common denominator would be 28. So that's 12 minus 7. And 12 minus 7 is 5. So 2/5 times 5 28ths. 2 goes into 28 14 times. I end up with 5 pi over 14 as my volume. And that's all there is to that one. All right, last example with the shell method. We've got this function here. It's similar to the reciprocal function as far as how it looks on a graph, which you could just type in your grapher. And we have we're going to wrap that around the vertical line x equals -3, which I have drawn over here. Here is this 1 over square root x function, and we only want to look at it from 1 to 4. So this little yellow region here is what I'm going to revolve around this vertical line. And you can see down here, there's a picture of kind of what it would look like after you revolved it around there and had a 3D shape. And so in order to use the shell method on this to get shells, I would need vertical partitions. So imagine a vertical partition drawn in here, and as you take that and wrap it around that line, you get this duct tape shaped figure. And a roll of duct tape, and a bunch of those, the shells made together. So if I have a vertical partition, remember vertical partitions always mean dx, and my formula is 2 times pi times shell radius times shell height. And so my shell radius in this problem is going to be the distance from here. Here's the line x equals -3, right here in the 3D picture, over to where my partition is. And so here, that's going to be the distance from here over to here. So I'll draw that in. Here plus here. So these two colors together, the red and the green, make up my shell radius. And so you know the distance from here to here is 3. And you know the distance of the green is x. That's the x value from here to here on that curve. So this point has an x value and a y value, and its x value would be the distance from here to here. And so I'm going to call that x, because remember, I'm doing this with respect to x anyway. So my shell radius is just 3 plus x. So I've got 2 pi and 3 plus x for my shell radius. Now I need to do my shell height. So the shell height is the distance from here to here, and that would be the y value of this point. But remember, I can't use y's, and so I want to use what y is equal to. Well, y is equal to 1 over the square root of x. So my shell height is going to be 1 over the square root of x, or you could say x to the -½ power. And so there is my integrand set up and ready to go. So if you take and multiply by x to the -½ we're going to have 2 pi 3 times, I guess actually let's just put that 2 pi out front. Go ahead and put it out here. And remember, your integral stacking from your partitions right here would stack from 1 to 4 as they spin around. So this is a 1 to a 4. And I'm going to have 3x to the -½ plus, and this would be like an x to the 2 over 2, times I add my powers and I get x to the +1/2. And so now I am ready to integrate. And so if I integrate that, I'm going to have 2 pi, add 1 to the -½ and I get 3x to the +1/2 divided by 1/2, which when you flip and multiply is going to make a 6, which we'll do in a second. And then the other one, add, and you'll get a 3/2 divided by 3/2, and then we'll flip and multiply. So 2 pi times 6 square root x. And then on the other one, you're going to have 2 square root x cubed over 3. And that is from 1 to 4. So now if we plug in our numbers, plug in the 4 first of all. I've got 2 pi. Plug in square root of 4 is 2, and 2 times 6 is 12. And then I have 4 cubed, which is 64. The square root of 64 is 8. 8 times 2 is 16, so I end up with 16 thirds. Subtract now. Plugging in the 1 would be a 6 plus 2 thirds. Alright, so if I simplify that, I'm going to have 2 pi times 12 plus 16 thirds minus 6 minus 2 thirds. So 12 minus 6 is 6. 16 minus 2 is 14, so I end up with a 14 thirds. Common denominator would be with a 3. So that would be 18 over 3 plus 14 over 3, which is going to give me 22 over 3 times 2 pi. And then that will give me 44 pi over 3. And so that would be your volume of that figure. And that's all for shell method.